So here we'll discuss about Wilkinson catalyst. So Wilkinson catalyst is such a type of homogeneous catalyst having common name chloridotris triphenyl phosphine rhodium 1. That means the oxidation state of rhodium in this catalyst is belongs to plus 1, and this is the formula RHCl PPH3O3. It is a red brown color solid compound that is particularly soluble in organic solvent that is belongs to hydrocarbon such as benzene. Benzene is aromatic hydrocarbon, and is also soluble in tetrahydrofuran. It is used as a catalyst for hydrogenation of alkene. Then for the preparation of Wilkinson catalyst here, we have to use rhodium 3 chloride hydrate. The oxidation state of rhodium is plus 3. Then triphenyl phosphine. Then we will get Wilkinson catalyst. And if you look at the reaction, the oxidation state of PPH3 is plus 3 in the reactant state. And after the product formation OPPH3, the oxidation state of phosphorus is plus 5. That means the change of oxidation of phosphorus from plus 3 to plus 5 means oxidation takes place, and hence it is act as a reducing agent and it will reduce the reactant rhodium 3 chloride hydrate from rhodium oxidation state plus 3 to rhodium oxidation state plus 1 D8 in the product state. And according to XRD shape, the XRD, the shape of the Wilkinson catalyst, that is a distorted square planar structure. And if you look at the total electron present in the Wilkinson catalyst, that is 16 electron. That means it is not satisfy the 18 electron. That means it is a coordinatively unsaturated complex. Hence, it will effectively bind with the substrate, that is alkene as well as hydrogen. Then go to the next step, that is very, very important. And if you look at the reaction, how the hydrogenation reaction takes place with Wilkinson catalyst. Then if you look at the Wilkinson catalyst RSCl PPH3 whole 3, there is a 16 electron, 16 valence electron is there. Then you have to add the substrate. When you add the substrate, one of the phosphine ligand will be dissociated and the substrate will be attached, and it will convert to 14 electron complex from 16 electron. That means these are 14 electron complex, and that is attached to the solvent, and the um, 14 electron complex generally highly reactive in nature, and it undergo addition reaction, that is oxidative addition reaction with hydrogen. Why oxidative addition reaction takes place? Because it is a coordinatively unsaturated complex. Then after oxidative addition, the next step, then the rhodium in plus 1 oxidation state will convert to rhodium in plus 3 oxidation state. Then it will react with a what, an alkene, and it will form a pi complexation reaction. And if you look at the pi complexation reaction, then the alkene will be coordinated to the rhodium 3 complex, and this will convert it to 18 electron, 18 valence electron, and this is called as intramolecular hydride transfer. And after that, what happen? The rate determining step you will get after the migration of migration of what, hydrogen, that is called as a migratory insertion of hydrogen, and that are carbon carbon double bond that appear in alkene, that will convert it to single bond. Then the last step is very, very important, that is a reductive elimination. After that, the reductive elimination reaction will takes place, the alkane will form, and finally you will get that complex in the form of 14 electrons. So this is the cycle. Now if you look at the cycle, first oxidative reduction will takes place, then pi complexation, then intramolecular hydride transfer, then reductive elimination, and migratory insertion followed by reductive elimination. So these are the following steps that involves, and these are the keynote that is very, very important in general. In Wilkinson catalyst, the rate of the reaction decreases with addition of excess PPH3. That means if you add excess amount of PPH3 during the reaction, the rate of reaction generally decreases. And it is observed that strong pi acid like ethylene act as a poisons by binding strongly with the electron-rich rhodium metal center and inhibit the hydrogen. That means if you look at the reaction, and when you have to go for reaction of Wilkinson catalyst with normal alkene, then that normal alkene will be binded, one of the pph3 ligand will be lost, and then further hydrogenation does not take place. It is very difficult because the Wilkinson catalyst generally binded by alkene, and it is hence the further hydrogenation reaction does not take place. Then the point number 3, the rate of hydrogenation decreases with the increase in the alkyl group substitution. That means by using carbon carbon double bond, when you go for the reaction of with the Wilkinson catalyst, there it is very important substitution along the carbon carbon double bond. And if you look at that, if the number of substitution will increases, then really generally increases the steric factor, and it is very difficult for this one Wilkinson catalyst for hydrogenation reaction. That means whatever the number of substitution increases along carbon carbon double bond, the rate of the reaction generally hydrogenation reaction generally decreases. And if you look at some examples, here two type of double bond is there. One is the higher substituted and another one the less substituted. The double bond inside the ring, that is the more substituted, and the double bond outside the ring, that is the less substituted. So definitely when you go for that type of reaction with Wilkinson catalyst, the regioselective reaction will be takes place. Wilkinson catalyst will be reduces the double bond outside the ring, because this will be less substituted and sterically less in the double bond are selectively hydrogenated. Similarly, when you go for the second one double bond is exocyclic and another one is endocyclic. And when both the double bond is there, exocyclic as well as endocyclic, the exocyclic double bond are selectively hydrogenated over the endocyclic. Then when you go for the third one, that is one is the cis double bond and another one is the trans double bond. Then what happens here, the cis alkenes are reduced more rapidly in comparison to the trans one. And the example fourth one, if you look at the compound, three double bond are there. Two double bond are isolated, that is conjugated, and another double bond are isolated bond. That means isolated double bond are rapidly hydrogenated over conjugated one. That means the conjugated double bond is not undergo hydrogenation reaction, but the isolated double bond that is will be reduced or hydrogenated very easily. And if you look at the next reaction, example number 5, double bond is there and triple bond is there, and when you go for the reaction, hydrogenation reaction in the presence of Wilkinson catalyst, then what happens? That triple bond, that terminal alkynes or terminal triple bond, that will be hydrogenated more easily in comparison to terminal alkenes. That means terminal alkynes will be easily hydrogenated in presence of terminal alkenes. And sixth one, when you look for the question number 6, then one nitro group is there, then carbonyl group is there, double bond is there. That means by using Wilkinson catalyst, not reduce any functional group like nitro, like carbonyl, it only reduce the double bond and you will get the product. Then question number 7, or example number 7, when you go for hydrogenation of reaction with a malic acid with a deuterium, give meso compound, and this is the meso compound. Similarly, with fumaric acid, you will get the racemic mixture. From fumaric acid, undergo hydrogenation reaction with Wilkinson catalyst, and you will get the racemic mixture product. Similarly, by using the alkynes and Wilkinson catalyst, the hydrogenation reaction will takes place and it will selectively give the cis alkene as the product. So these are the some of the important uses of the Wilkinson catalyst. Okay, so thank you.